Welcome to the next installment of the Cooperative AI Foundation's seminar series on new directions in cooperative AI. So my name is Jesse Clifton. I'm a research analyst at the Cooperative AI Foundation, and I'll be hosting the meeting today. So before I jump in and introduce our speakers today, just a little bit about the seminar series. So we're hosting seminars every 2 weeks, and the idea is for a thinker to offer their vision for research directions in cooperative AI, in particular kind of high impact research directions that the Cooperative AI Foundation might be interested in supporting. So these are a little bit different in flavor from your normal academic talk, in that they are explicitly agenda setting. We want people to give a kind of high level vision for a research direction that could absorb a lot of talent and resources from researchers in the cooperative AI space. So we are currently accepting proposals on a rolling basis to give a talk. Because this is maybe a bit of a more burdensome talk to put together than usual, we'll award a $5,000 honorarium to those who are applicants who are successful. So we strongly encourage you guys to apply. As for today's session, our speaker is going to be Joel Leibo, and he is going to be talking about how to measure and train the social cognitive capacities, representations, and motivations underlying cooperation. So Joel is a research scientist at DeepMind. He got his PhD in 2013 from MIT, working on computational neuroscience. But now he is working on the question, how can we get deep reinforcement learning agents to perform complex cognitive behaviors like cooperating with one another in groups? And after Joel's talk, we'll have a discussion that will be kicked off by our two discussants, Natasha Jaques and Marco Janssen. So Natasha is a senior research scientist at Google Brain and a visiting postdoctoral scholar at Berkeley, and her research is in social reinforcement learning. And Marco is professor in School of Sustainability at Arizona State and director of the Center for Behavior, Institutions, and the Environment at Arizona State. And Marco works on collective action problems, in particular those affecting global challenges like climate change. Without further ado, I will stop sharing my screen and hand it over to Joel.
So here's a slide to start with, showing all of my brilliant collaborators on all the things I'm going to talk about today. Most of whom are at DeepMind, a little bit at Brain, and a few collaborators in other places, but mainly we're going to talk about this kind of work with these people today. We want to build cooperative AGI, and this is a talk about the quest for AGI in particular. By that, I'm emphasizing the G, the artificial general intelligence it stands for. So it's not really a talk about narrow artificial intelligence applications or near-term things. It's really more of a long-term vision for how we build a general purpose artificial intelligence that will be cooperative and aligned and good. And if you get nothing else from the talk, the highest level point in here is that social environments in particular are a stress test for artificial intelligence generalization. And they have certain kinds of special structure that would be very hard to capture or even address in a solipsistic approach. I tend to use the word solipsistic as a kind of a pejorative to mean single agent artificial intelligence methods. So what I'm really saying here is I'm saying that once you have a social environment involving other agents, there are all kinds of latent structures that you can take advantage of, and also can pose problems that you can barely even know how to address if you were in a single agent. There's just an environment that you can't say anything about kind of framework, the solipsistic framework. Okay. And I'm going to argue that the way we should approach building a cooperative artificial general intelligence is by reverse engineering human intelligence. It's a tired point, of course, to say that humans are amazing. Humans have accomplished a lot if you compare us to other animals. We have We have technologies and cultures. We span the globe. We cooperate with each other on even individuals we've never seen before and never are not related to us that might live very far away from us. No other animals do this kind of thing. But of course, human intelligence isn't all positive. There are certainly negative things that we don't want to emulate about human intelligence. There are wars, there are other problems, and we need to have an intelligent view of reverse engineering human intelligence as the goal, where we reverse engineer the parts that we want, the parts that are good, the parts that give us cooperative artificial general intelligence in the way we want it to, but we try not to take the parts that will, the dark side of human intelligence. I'll come back to this at various points throughout the talk. So taking a reverse engineering perspective on human intelligence in AI is very common in other parts of AI, really more often in the parts of AI that study the more classic cognitive abilities, things like perception, attention, memory, planning, the more kind of cognitive neuroscience inspired AI approaches. These are very common. What I'm proposing is conceptually the same. It's still about reverse engineering human intelligence, but it's about reverse engineering the social cognitive capacities, representations, and motivations, rather than these solipsistic cognitive abilities like perception, attention, memory, and planning. Now, we may also need those, of course. It's not necessarily an either or. It could be a both. But most of the time, when people are talking about the goal of reverse engineering human intelligence, it tends to be a more solipsistic kind of line of research than the one I'm proposing. So humans are an ultrasocial species. There's many ways to illustrate this. I really like this paper from 2007 by Esther Herman and Mike Tomasello and many others, where they were comparing, they came up with kind of intelligence tests that are well controlled if you test them between humans, 2.5-year-old children, chimpanzees, and orangutans. And these are the actual tests are kind of listed in the upper right part of the slide here. They're things like tracking a rewarding object after it's moved, like object permanence kind of things, rotating things, things that are effectively addition and relative number stuff, some causality things with noises and shapes, stuff you can do with a 2.5-year-old child or a chimpanzee. That's the physical intelligence part of the test. They also have a bunch of tests that were more social intelligence things like social learning, communication, theory of mind tasks, like there's gaze following, some intention inference kind of things. And they give this whole battery of tests to their 3 cohorts there, the humans, chimpanzees, and orangutans, and they find that in the physical domain, the children are really pretty much on par with the chimpanzees. We're a little better than orangutan, but about the same as chimpanzee. It's only in the social domain where the children are doing much better than the chimpanzees and orangutans. And so the implication that this paper and many, many others draw from it is that there's something early on in our development, maturation, that even you see it in 2.5-year-olds, is already different in our social intelligence, but not necessarily different in other kinds of our intelligence. So we're maybe similar to other primates along those dimensions. But the fact that we have differences in our social intelligence let us cooperate in different ways, which let us learn from each other in different ways. It lets our culture accumulate, and then eventually we have language and culture, and we can do much more in all domains of intelligence, not just the social ones, of course. We also learn geometry and mathematics and engineering, and we can build technologies, and we do all of these things as a consequence of our initial difference in social intelligence. And this is sometimes it's called the cultural intelligence hypothesis or other versions of that. The idea is that our niche as an animal has really always been one that is like intensely social and it's like obligatory for us as a species. We can't really survive on our own without others much at all, without learning how to do so from others. So So I'm going to talk a lot about this term, social cognitive capacities, representations, and motivations was in the title of the talk. I'm going to start abbreviating it as SCCRMs because it's a bit of a mouthful, social cognitive capacities, representations, and motivations. First thing I want to say about it is, why is it such a mouthful? Initially, I was thinking about the idea for this talk, and I wanted to say something like cognitive ability. I wanted it to be analogous to what you usually have in a reverse engineering research program. You would talk about the cognitive abilities that you want to capture, like perception, attention, memory, planning, things like that. And then I said, well, but they're not exactly, cognitive abilities sounds like the other set. So we need something that's more social, more cooperation oriented. So I said, maybe they should be called social cognitive capacities. But then I thought a little further about it, and it's like, well, they're not all really capacities at all, actually. A lot of things that underline our cooperation are probably more like representations and motivations and other kinds of things. So we ended up with this bit of a mouthful term, the social cognitive capacities, representations, and motivations, the SCCRMs. So for reasons that I'm going to talk about later, it doesn't completely matter. We don't have to take a strong stance, like an assumption type of stance, on what exactly the list is. It's going to be fine to explore lots of different hypotheses here, but I won't put up this slide at this point in the talk just to kind of fix in people's minds like what kinds of things I might be talking about. It doesn't have to be these particular capacities, representations, and motivations that are on the slide, but these are some example things that it might be that are important. What we're really looking for is what is important for human intelligence, and what do we have to build into artificial intelligence in order to make it able to cooperate the way humans do. So kinds of examples might be the mind reading capacity that we have. It's also called theory of mind. There's also communication abilities. We have empathy. We have the ability to imitate. Those are kind of capacities we might be talking about. And that doesn't mean these things are necessarily distinct from each other. They could be overlapping. This might not be the best way to carve nature at its joints, the way I've written it here. We can talk more about that later. Also, some of the things that matter are probably more like representations. People represent social relationships. So you can imagine this kind of a graph of how you're related to everyone else and how they're related to each other. And you might represent all that and reason about it as you make decisions. You can plan with respect to it. We also represent social groups, and we have markers of social identity. We understand who's in which social group and what that might mean for our behavior and other things. And we can remember individuals and have our history of interaction with different people. It's very important for things like if you want to have reciprocity with them or something like that, or track their reputation. Also very important are social cognitive motivations. This includes everything from social rewards, like being rewarded by seeing someone else smile at your action, as well as these emotions, things like anger, fear, envy, and shame. These all have lots of implications for our social intelligence. So the point of talking about the SCCRMs is that they underpin our complex social behaviors. They are key to the secret of humanity's success. There are many different social behaviors that are important. This is obviously a very incomplete list on the slide here. There's things like reciprocity, reputation, division of labor, cumulative culture, our sophisticated language, the ways that we can monitor and sanction each other, and the kind of origin of institutions, as well as social norms, and then coming toward our technologies and industries and things like that. All these things are underpinned by the SCCRMs, I'll argue, and much more, of course. So that's kind of basically the space I want to be talking in. This is it's aspirational, of course. This is what we'd like the research program to ultimately be able to capture. So, right, we're going to reverse engineer human intelligence to build cooperative AI, cooperative AGI, really, artificial general intelligence. Okay. So the most important point in this talk is that in multi-agent settings, there's the demand for generalization that an agent faces in reinforcement learning can always be decomposed into two sources. There's the variation in the world that comes from things that change over time in the physical environment, like the lighting changes, you go different places, you see different scenes, and agents need to be able to cope with that. But also there is a social environment. The social environment is you meet different people and they act differently and you have different relationships with them. Sometimes you cooperate with them, sometimes you compete with them, and you have to know what is going to happen with different people that you meet and how to act appropriately in each situation. Sometimes you go places and there's different social norms. You need to be able to figure out what they are and act appropriately. Of course, in real life, you have to cope all the time with both physical and social environment generalization, but we can decompose it a little bit. We can talk about them somewhat separately. Now, in solipsistic AI and solipsistic reinforcement learning in particular, there's a view where you separate things. You say we have an agent and we have an environment, and kind of never the two shall meet. You don't make assumptions about the environment when you're working on the agent. And so you're kind of left with a world where you really only can study physical environment generalization, because there's not much way to have a social environment without kind of, you don't have it in the simulator when you do that kind of work, unless you have other agents that are kind of already in there, but that's not the way it typically comes about. You have like a game that is kind of static. But in a multi-agent setting, you'll have other agents that are learning at the same time. And then there's lots of structure you can say much more about. So to proceed in this research program of reverse engineering human cooperation to build multi-agent artificial general intelligence, we have two methodological questions very broadly that we have to settle. Really, there's training and testing, just like everything else in machine learning and AI. There's questions about training and questions about testing. I'm going to actually reverse them and talk first about testing. And this is where I'll introduce Melting Pot. Melting Pot is what I'm going to talk about for much of the rest of the talk. Melting Pot is an evaluation protocol and a suite of test scenarios for multi-agent reinforcement learning, which is an approach to building artificial general intelligence that should be cooperative. That's the hope anyway. So Melting Pot specifically tries to evaluate social environment generalization. Now, of course, you can never fully disentangle things, but the goal is to isolate social environment generalization from physical environment generalization. So now I'll speak about how the evaluation works. So Melting Pot evaluates algorithms that produce populations of agents. Now, you might think that that's some kind of strange thing. That's not how most reinforcement learning algorithms work, but actually it is how they all work, or they can all be made to work that way. All we mean by a population of agents is some distribution over policies, which is not much different from anything else. It could be a very simple distribution that just gives maybe you create only one policy and your distribution just says, give me that one policy back when you sample it. So it's meant to be general enough to encompass, if you just run you could run a solipsistic single agent reinforcement learning algorithm, and that would be fine. Or you could run any more sophisticated multi-agent method. All of them can be seen as producing a distribution over policies in the end. So anything that does that, Melting Pot can evaluate. So you train your population using your method, whatever that may be. We make very little assumption about it at this stage. And then we test it using Melting Pot. So what would success look like from a benchmark like this? So to do well in Melting Pot, when we sample individual agents or sets of agents from the population that you produced, they should perform well in a range of different social situations where the individuals that we sampled are interdependent, and there may be other individuals in the test as well. That's the second point there. They have to generalize to interact effectively with unfamiliar individuals that they've never seen before. So you're going to do some kind of training. Maybe it involves some sort of population self-play where you meet other agents in the focal population. I'll start using that language. And so they're familiar with each other. And then at test time, the focal population will be mixed with another population, the background population, which will contain unfamiliar individuals that they've never seen before. No agent has ever seen before. So it's a test of social generalization in situations where everyone is kind of interdependent on each other. It would be a bad test if you just kind of have something where you're just you're playing a computer game alone in a room and you have no connection to the other players. That would be a bad test for Melting Pot. It should be something where they're more interdependent. Like what I do affects what you do, or what one agent does affects the other agents. So Melting Pot is divided into test scenarios, a bunch of different test scenarios. We have some more than 85 of them right now, and there's more coming out soon. So each test scenario has two parts. There's what we call a substrate and a background population. The substrate is the physical environment, like the kind of raw physical environment. This includes like the layout of the world, what the rules of the game are, how physics works in this world, everything like that counts as part of the substrate. If you're kind of coding it in a computer game language, then it's everything that the game engine is handling for you would be there. Then there's also the background population. This is everything with agency in the world. And the way we do it for Melting Pot is these are all also reinforcement learning agents, but ones that we pre-trained and we froze at a certain point. So they are just fixed policies from the perspective of new agents that we'll be playing, but they're going to constitute a particular test. It'll make it much more clear in a second. So everything in Melting Pot right now is a 2D environment, like the ones that you see right here. There's nothing forcing it to be 2D. In principle, it might not be 2D. In the future, we might add 3D things. But for the moment, it's 2D. I should also say that this is all open source now. Melting Pot is available online. There's a GitHub page. You can look at it yourself. You can use it, everything. And so also everything there right now is 2D, of course. I can talk more about other things later. But so the way it looks at the moment is everything in there is a 2D world where it's a partially observed Markov game. So agents see not this whole screen that you're seeing there in the corner of the slide, but they actually see a kind of window around themselves. They have an orientation, so they don't see like isotropically around themselves. They actually just see in the direction that they're facing, mainly. So we kind of think of it as like 2.5 dimensional rather than really 2-dimensional because it's got this kind of orientation to it. It's partially observed, and so it has many of the same issues that you face in a 3D world. Yeah. The size windows that we typically use are 88 by 88 pixels in RGB, so it's comparable in size to the way people look at Atari for single agent reinforcement learning, a similar sized windows, but now per agent, of course. Each agent then is so you have much more if you count all the agents. At test time, you have to test in decentralized execution mode, but we make no assumptions at all about how you train. So you could do centralized training and decentralized execution, which is a very popular paradigm that's supported here. And the numbers of players in the different games range from 2 to 16. Most of the games have around 8. So I'll walk you through the evaluation protocol now. So you start with a substrate, which is the physical environment. If you're a researcher, you have a new idea for your new agent, you want to train it here. You run some self-play algorithm, some kind of algorithm using the substrate, which gives you it's a simulator really. You have a physical world. You can plug agents into it, and they can do some training. And then you get a distribution of agents to sample, and then you take the agents from the focal population you just trained, and you mix them with background players in particular scenarios that constitute specific tests. So the idea is, well, that we chose the background populations for the test scenarios to be specific things like that are kind of a priori interesting. So if the game were Prisoner's Dilemma, then you might have one test scenario where it's playing with cooperators. And then, well, if it's Prisoner's Dilemma, I guess the right answer then would be to defect on them, which that's maybe not the best test. We don't actually have something exactly like that. But if you then had one where the background population was playing a tit for tat kind of policy, then the right thing to do would be to cooperate with them, and that would be how it worked. But they're all much more complicated than just matrix games like that. So why is this challenging, and how could it possibly succeed? Is what this slide's about. So if you think about a game like rock paper scissors, say, if there was dynamics like that, where if I play rock, then you could beat me by playing paper, and then I could beat you by playing scissors, and you could kind of cycle around like that. In order to do well at test time, if you're going to be tested with different specific populations, like they might play rock in one scenario, they might play paper in another scenario. You have to, but you don't know what those players are going to do beforehand. You can't see them during training. So during training, what you would have to do is have some kind of scheme where your algorithm is going to generate its own diversity to play against. So your algorithm would have to, on its own, figure out that, oh, in this world I can play rock. Also, in this world I can play paper, and in this world I can play scissors, and learn how to be general over that space in order to then adapt to test time to play with whoever it's playing with. If it were actually rock, paper, scissors, it's like one-shot rock, paper, scissors, there'd be no time to adapt. But these games are not like that. These games are kind of more temporally extended things where you walk around in a world and do something, and it then has similar incentives to something like rock, paper, scissors. So you can see like, oh, the other player is starting to play rock, so I'll start to play paper, and that's how it works. An important thing is it doesn't mean you should always play Nash equilibrium. It definitely does not mean that. Okay, so onto the training side. So The guiding principle in constructing Melting Pot was that we shouldn't make design decisions that will restrict too much the scope for creativity and how researchers can train their agents. So we really try to be very agnostic what happens in training, and then everything else is kind of organized by the fact that we have a single test. Everything will be tested in a like for like way, so you can do whatever you want during training. I like to talk about this in terms of things like inductive biases and questions about nature versus nurture, because we can kind of sidestep them, I think is the point. It's not that they're not important. It's a reverse engineering approach, after all. We do care about whether human cooperation is, any particular aspect of it is due to nature or nurture. That kind of is in scope as a question, but Melting Pot, the evaluation protocol, doesn't take a stance. Melting Pot just says, we have a single rigorous evaluation, and you can make whatever hypothesis you like about, say, theory of mind is, it has to be built in as an assumption. It's an inductive bias in order to learn something else, or maybe it doesn't, and it's supposed to come out of the emergent properties of some more general learning. You can make any assumption on whichever side you like, and test the algorithms that come out on the same exact way across all those different kinds of choices. So it's pragmatic, right? The evaluation lets us avoid taking assumption level stances about things like what are the right inductive biases. And I think it's the right thing to do if we ultimately want to figure out what inductive biases you need. So one way I like to talk about it is this kind of pragmatic principle of we're searching for the minimal set of maximally general social cognitive capacities, representations, and motivations. And I think that's really the right way to see it. We want to build artificial intelligence algorithms that can recapitulate human-like cooperation, but we don't want to build in necessarily every single idiosyncratic aspect of human cooperation. We want to get the minimal set of maximally general things. Of course, I'm going to kind of sprinkle open questions throughout this talk. There are millions of interesting questions we could ask about humans, like what is the right list of human social cognitive capacities, representations, and motivations? Like, can we kind of carve nature at its joints, if you will? And that would be answering questions like, well, is mind reading really distinct from, I don't know, emulation or something? Or are they, somehow linked together in some way? You need to figure out like what's redundant or what's not. It's like a basis for the space. And that's definitely interesting. We might not need to know it exactly for our artificial intelligence research program, because you can kind of have an overcomplete representation if you want. We don't necessarily need to know the exact like minimal list. We need something that covers the space. Other questions that are interesting for humans are like, to what extent are the human social cognitive capacities, representations, and motivations specialized for social cognition, or are they just general purpose cognition being used in a social domain? That's very interesting. You could also ask, of course, where and how these things are implemented in the brain, or how they interact with social norms and culture, and how they're different in different places around the world, if they are. You can also ask about if there's connections to different disorders, like maybe autism and psychopathy can give you some interesting leverage on the what these capacities are, how they work, and how they can go wrong. And of course, there's tons of interesting questions about how and why they evolved, like maybe group selection is important, maybe it's not. And you can also ask the more kind of historical questions about whether they were new developments during hominin evolution, meaning like since our evolution since our last common ancestor was something like a chimpanzee. Were they kind of new developments at that point, or were they more like elaborations of mechanisms that we would share with other primates? These are really interesting questions. They're definitely relevant to a reverse engineering research program, but for us, they're more like hypothesis generating devices. Like we can read the latest literature on this in humans, any of these questions, and use it as a way to generate a new hypothesis for a new multi-agent reinforcement learning algorithm, which we can then test in the same way as all of the rest of them, and see whether it's actually improving scores on Melting Pot, and see if it's improving our movement toward cooperative AI. Yeah. Another interpretation, coming back to the training protocol now, another interpretation that I like of what's actually happening during Melting Pot training is when you train in self-play or anything like that, you have a bunch of agents that are solving some kind of problem together. Maybe they're managing resources, maybe they're building an irrigation system. They're learning to kind of do something in a world in the presence of one another. And you can see this as creating like a little artificial society in very miniature, and then testing it by mixing that society with other societies in a, and we have different kinds of tests that we look at. Some of them are kind of, we call them resident mode tests, where we have many agents from the focal population in the test meeting a small number of background agents. So like there's some few that are visiting them, maybe. It's like, how do you act toward visitors or something? And then separately, we have visitor mode tests, where you maybe trained a whole large focal population, but we're going to take just a small number of samples out of it and mix it with a large background population. So that's like how your agents that you trained act when they are the visitors. And both of those are interesting. And we make these kinds of choices in a very kind of case-by-case way in order to, for particular substrates, to ask particular questions that are like a priori interesting for that substrate. So I'll do this kind of semi-extended example here to talk about, make it much more concrete now how it actually works. And so this environment was partially inspired by a paper by Marco, who's here as one of the discussants, and many other papers from his lab as well. I know we're following up on it. So this is the direction that we took the environment anyway. So we call this substrate commons harvest, and agents move around in a two-dimensional world. They are rewarded for eating apples, and they have a partial viewing window, as I said before. The thing that is specific to this substrate is that the apple growth rule is density dependent. So the apples will grow faster if there's more apples nearby them. And if you remove all the apples in a local area, then that area will kind of die out and there'll be no more, they'll never grow back there. So episodes last for 1,000 steps, after which the game will reset to its initial condition. So it's modeling some kind of renewable resource. So it's not like if you destroy the resource once, then it's gone forever and you never get another chance. This is like one where if you wait a while, then it comes back again. It's some kind of renewable thing, but it's still bad to deplete it locally in time. Also, agents can zap each other with a timeout beam, and if they get hit, they get removed from the game for a while, which is going to be important as a way for them to sanction each other. So as a single player game, this is a very easy reinforcement learning problem. This is what it looks like. I hope everyone can see this video. This is an agent just running around, eating apples, perfectly happy. It never depletes its resources because it has learned that that's a terrible idea. And if it does it, then it won't get any more apples until the end of the episode. So it's a very easy problem for a single agent. It just comes up with a policy like this. And if I can go to the next slide. Okay, but with multiple players, it goes very badly wrong very quickly. So that was very fast. I don't know how much people could really see it, but as soon as the episode started, the 6 agents here ran up and immediately ate all of the apples, and they were all gone. There was nothing left. I'll play it again. There they go. It's just they are super efficient at eating it, but they just immediately eat the whole thing. There was nothing like the kind of nice back and forth waiting for things to regrow that we saw in the single agent case. One way to solve this is you could have agents that can sanction each other. We have different ways of kind of motivating them to do that. One that we did was from this Fair and Schmidt model of advantageous inequity aversion. If some agents sanction others, then they learn to not overconsume, and then that makes them solve it. There's of course many other ways to solve this problem, like one from Natasha as well. And I was going to, should I just talk about this quickly? So one thing that we know is that in environments like this, if agents can exclude one another from if they cannot exclude each other from accessing resources, then you'll typically get social dilemmas. And so in the version we just looked at, they were unable to do that. They can't really stop each other from grabbing apples that are anywhere around. So they can't really trust that others are going to not just eat the apples nearby, so they might as well just eat them all as quickly as possible. There's no point in being kind of sustainable about it. But in this one, there's now this kind of these walls, and they can zap each other as they go down the corridor there. They learn to actually exclude each other from entering the areas where the apples are, and you'll end up with one agent in there at a time. And then they've kind of converted this multi-agent problem back into a single agent problem, which is one that is kind of easy to solve again, for the same reason that it was easy as a single agent problem. So this isn't really a solution that we like exactly, because it of course creates inequality, but it is sustainable. It's probably not the best solution we could hope for though. But we can also ask, this is also a very like kind of strict case. Like it's like there's like one single entrance. It's like the exclusion strategy can emerge endogenously, but it's like very easy for it to happen. What if it's like slightly harder? Here's a case where, so now the only thing that's different is that there's no wall in the middle now. And so here, the right thing to do is for two agents to go into that area where the apples are and both defend it and act sustainably. And this is what it would look like if they were successful. But in this case, we actually basically cheated to get these agents to do the right thing. And no actual reinforcement learning algorithm that doesn't get extra information can do this, can learn this strategy. What they all actually look like is more like this, where you're just going to see another tragedy of the commons kind of thing. The real issue here is that they don't trust each other. They can't, even though it's like really very much in their mutual benefit to just work with the other player that is in the apple area, they do not figure that out. We also see this in other environments. We have some trade environments where they're unable to learn to trust each other, even when it's like very much in their benefit to do so. And I wanted to make sure I get to this. So trust, I think, is an open question. That's really the point here. Like, how can we get agents to trust each other? But not, and I think trust would be is an important thing we should put in, but not all human social cognitive capacities, representations, and motivations are like as obviously important as trust. Some of them are potentially unpleasant or negative, might have negative effects on society, like things like anger, anxiety, guilt, shame, but they also still might be critical to human like cooperation. And you can see why if you think about maybe anger is part of a deterrence strategy, and deterrence is of course a way to prevent conflict. And so a question arises, should we build motivations like that into our AI systems? It seems a bit strange. I don't have the answer here, but I think it's something we need to grapple with in a reverse engineering research program. I had some other open questions, but maybe I'll see if they come up in the discussion so we can have a better discussion, I guess. I did want to end on this one point though, at the end. So eventually, probably not today, but I think eventually it will make sense to organize some kind of competition with Melting Pot. It's all open source, available. We could have a competition where different teams submit their best algorithms to be evaluated in comparison with one another. Competitions like this have a long history of being useful in both machine learning and in game theory. Everything, there was Axelrod's tit for tat competition, the competition that tit for tat won, it's very famous. There's of course ImageNet, which is kind of the thing that kind of launched the deep learning revolution. And structurally, since this is a test of generalization, it resembles the big supervised learning competition. So there's lots of reason to think that it could work well. Probably one thing you would want to do in setting this up is you would create brand new test scenarios so no one could cheat. Like it would be like totally never before seen melting pot test scenarios that would be created just for the competition and only like at the final test point. So no one could kind of do graduate student gradient descent on the hyperparameters of their algorithms to do better. And I guess I'll leave it at that. So I have plenty of other slides, but that's probably a good point, right?
Yes, I think that's a great stopping point. And thanks so much, Joel. I really enjoyed the talk and I'm looking forward to some discussion. And on that note, we can turn it over to the discussants. Natasha and Marco, maybe Natasha can take it away, and it's fine if there's a bit of back and forth between the discussants and Joel, and after that we can open it up to an audience-wide discussion.
Great, thanks. Great talk, Joel. I really enjoy this, and I've been checking out the melting pot benchmark. I'm excited to use it. So I noticed one thing I want to comment on is I noticed in your proposal you mentioned that in terms of selecting what social cognitive abilities are being tested by melting pot, you said it's better to be over complete than under complete in case there's something important you just don't want to miss it. But I wonder if, because this is a benchmark, you're kind of making choices about what the benchmark is testing. People might have a tendency to just try to maximize average performance across all of the games. So if you tend to select games that overemphasize a certain ability, they'll end up focusing on that, right? And if we think about like the Cooperative AI Foundation mission, which is like improve cooperative intelligence in a way that benefits humanity, maybe there's certain abilities that are more important than others. Like you could imagine that like improving the social cognitive ability of understanding property or ownership is less important than improving like trust, right? In terms of if we care about problems that could benefit humanity, maybe I'm thinking about solving cooperative challenges related to climate change, for example. So could you comment a bit on that?
I think it's a bit hard to know a priori which ones are the most important. And I think the reason I shy away from making these choices of like, you know, this is the important one, is just that it's like kind of epistemologically difficult to be sure. Is property and ownership less important than trust? I don't know. From one perspective, it seems that way, but maybe it's such an important organizing principle that our, you know, so many institutions couldn't work without it, and we need these institutions to cooperate on larger scales, and that's really, maybe that's the secret of our success. And trust is just some epiphenomenal thing with oxytocin, or you know.
That makes sense. Okay, and the other thing I want to,
really, the main point is that it's we have to be kind of humble about this, and we shouldn't let our assumptions be too overriding on it. It should be an empirical methodology where we have a set of environments and we have a set of we have algorithms that we're trying to distinguish from one another, and we want it to have a benchmark so that when people submit new algorithms for their new ideas, they're actually meaningfully getting different scores from other algorithms that are different from each other. It's like that. That's how you kind of tell. Like if these two things are redundant, then that means that probably all the different algorithms we've tested on them are getting the same scores, or they're all missing the same thing, or you know, that sort of space.
Okay, so it sounds like you're like open to revising which tasks are tested based on maybe feedback from stakeholders or whatever. So I guess the other thing I was noticing is that. Oh, sorry, what was that?
It should be a constantly evolving open project where anyone can submit both new algorithms and new substrates and new scenarios.
Nice. Okay. And yeah, I was noticing that a lot of your open questions seem to relate to questions about like human social cognitive abilities and how they arise and what use they provide, right? And so I'm just curious if your main goal for Melting Pot is actually kind of feeding back into understanding human social cognition, or is it about developing, you know, AI algorithms that are better able to cooperate or have better social abilities? And to what extent do you think those are overlapping versus opposed?
I think they're overlapping, but the primary goal here is about AI, very clearly.
Okay.
Because the ultimate deciding factor is a performance one. It's about measuring cooperation in a certain way and saying that these agents are cooperating. It's not about asking like, is it cooperating exactly the same way that humans do? It's just about that. It's like, you know, you make a hypothesis about this particular inductive bias is important to have inside the agent, and then it'll cooperate better, and it will or it won't, and that's what settles it. It doesn't actually tell you anything about whether humans do it that way or not. You could hope that maybe like, well, we got it to work in the agent, that tells us something, maybe we should care more about it as a hypothesis for humans, but it doesn't actually answer that.
Okay, that makes sense. And I don't know how much time I have left. Maybe I'll just stick to one more question. So the thing I'm really excited about is testing cooperation with humans, right? Because I think if we want to make AI that's useful, we probably want it to be able to cooperate with humans. So I was actually like looking into the GitHub for Melting Pot and checking it out. And I see you have like a script that you can play with it interactively, but are you planning in the future to support like making it easier for people to run human subjects experiments at a larger scale, like kind of launching things on MTurk or something like that? And then the other sort of related question is,
yes, basically. We do want to do that.
So that's just a yes. Okay, that's good, because that's what I want to do. And then the second thing is like, I think cooperating with humans has a lot of really interesting, rich aspects, right? Like I'm sure you're familiar with this paper out of Berkeley where they were looking at Overcooked, and they train a behavior cloned model of the human and they test all their algorithms against it. They get a beautiful graph like, oh, are things better than the baseline? Beautiful, beautiful. Actually deploy it to real humans, and those differences just disappear because the human sort of adapts for the weaknesses of each agent. So you can't really even understand what's going on. So have you thought about this kind of tricky aspect? And do you have any comments on how to deal with humans adapting in this way?
Yeah, actually, can people still see my slide, the one that I'm showing right now?
Yeah.
Yep.
The two approaches that are on listed there, the 2 bullet points are actually the 2 things you just talked about, really. On the one hand, you could, in melting pot language, you could distill the human performance, like have humans play the game, distill it into an agent algorithm, behavioral clone it, and then have that be another test scenario. But that's like a static one now. That's one thing.
Right, but that was the Berkeley paper. They see that doesn't generalize very well. Yeah.
Yeah. So then the other thing you can do is actually just at test time have humans play it, and then they become just another algorithm you're comparing, like any other algorithm you're comparing on the benchmark. And I think we want both because sometimes the static one is just going to be much more convenient, and also a lot of the work of setting up one is the same as the work of setting up the other. But
thanks.
Yeah, thank you, Joe. I will also, I think my questions are kind of following nicely through this because my interest is how humans make decisions. So doing human subjects experiments in these more complex environments, and then try to typically use agent-based models to kind of explain those data. This was really a nice talk, but I have a few questions that I think address more about the connection with human subjects. It seems that all the experiments that you're, all the kind of games you're included, do not include kind of communication. And in a lot of our work, we find that without communication, it's very difficult to get any cooperation. And and an open question that we have is, why is communication really so effective? We have various projects trying to understand that, and that might also be a challenge if you start having the bots interacting with humans, because the moment humans may identify the bots as bots and not as humans, they may change their behavior. So the role of communication becomes quite critical, and I wonder whether you have thought about that.
Yeah, lots of, so communication and language are the topics at hand now. So we're thinking about this from a bunch of different angles, sort of simultaneously. Just on the final thing you said about whether it would, if we have bots playing with humans and the bots don't talk, then the humans will just pick up on that. It'll break everything. They wouldn't cooperate the same way because they couldn't talk the same way. That's maybe true for the moment, but I don't think it's actually going to stay true. We have now large language models that you can sample from, and they produce very convincing text. So effectively the machine learning models can talk these days. It's of course an open question how to get that kind of language model integrated with these more kind of embodied simulations. There's a simple grounding problem, but I don't think it's an insurmountable one. I think it's one that we can make a lot of progress on. So it's not like it's going to be forever these two lines can't meet. Like the agents that we trained will be able to play with people. It's a bit Turing test-like at that point. So it can work. But we're also approaching it from other directions as well at the same time. There's a line of work on more just more restricted communication that can pass between agents, where it's, you have some particular semantic channel, like a reputation channel we had. So the one time we did an experiment with human subjects on these kind of environments, that was how we did it. The thing that's on the slide right now in the lower left corner is actually, that's like the view that humans had, where they saw kind of they saw everyone's reputation basically, which had to do with how much they were contributing to something public good like. And so that was one thing being communicated, maybe modeling, as if they were gossiping about it or something like that. But it was just that one bit of information that was passed around. And that's a way to cooperate. They can cooperate using that, both humans and the agents. So that's another line. There's another line as well. There's a bunch of lines here that are more about emergent approaches, where agents can kind of come up with their own language, where they have several kind of meaningless signals that they can send, and they can learn to attach meanings to them. And right now, at the moment, we don't have anything specifically targeting that in Melting Pot, but we soon will. And
so that's actually a lot of the when we do the empirical work and trying to code what it is that makes that humans cooperate. It's not that the language is necessarily meaningful, but I think it's often to identify whether the others are people like themselves or are nice people. And actually, from a lot of the coding we have been doing, we find that kind of the type of language, whether they are nice to not cursing to each other, is more important than the content itself. So yeah, I can imagine that you can create in that way. But that will be an open question about what kind of language if you have kind of talking bots, whether they will be convincing enough for to cooperate with agents. So another, because you also mentioned motivation, and I saw in your slides also the work of FAIR. A lot of the kind of motivations that we see that affect the level of cooperation is related to inequality and justice, and also when we see what people are communicating about, or why people are cooperating, if they talk about why they end up cooperating, is as related to what we call procedural justice. So I wonder whether that is something you have thought about too.
I'll jump in before Joel answers, because we are at the end, the hour end. We can continue the discussion informally, hopefully afterwards. But for the kind of official closing, I just want to thank Joel and Natasha and Marco again so much for the time and thoughtfulness you've put into this. And a few things to put on everyone's radar before we close. Natasha will actually be giving her own talk later in our seminar series. And if you thought that the parts of Joel's talk about evaluation and what kinds of cooperative or multi-agent capabilities we might not want our agents to have, you might be interested in a talk I will be giving later in the seminar series on so-called differential progress in cooperative AI. So how do we make sure that we're making our agents able to cooperate better without making them much better also at, say, deception and manipulation and things like this. And finally, as Louis and I said at the beginning, we are accepting applications for people to give their own seminar talks, and certainly encourage you to apply if you think that you have a vision for the cooperative AI community. Thanks so much.